Hello, welcome to another module of this course Analog Circuits. So, in the past few modules we had been discussing about multivibrators. We covered the bistable multivibrator and then the astable multivibrator. So, in this module we will be covering the monostable multivibrator. Now, before going into the description of a monostable multivibrator using an op-amp, first I want to just refresh the concept of the monostable multivibrator. So, monostable multivibrator is a multivibrator that has two states, a circuit whose output can be in two states just like the other two, that is the astable and the bistable multivibrator, but the difference between the other multivibrators and a monostable multivibrator is that only one of the two states is stable. So, by stable I mean if the output is in that stable state, then it will continue, the circuit will continue to remain in that state unless it is disturbed externally. In the other non-stable state, however, if the circuit is present, then the output will over time shift back to the stable state. So, that is the basics of a monostable multivibrator. So, let us see what are the details of the monostable multivibrator. Okay. So, it has two states just like the other two multivibrators, but suppose I call the state 1 as the stable and state 2 as the non-stable state. Then over time the circuit will transform from state 2 to state 1, but if it is in state 1 it will continue to be in state 1 unless it is. So, state 1 to state 2 transition will happen only on external trigger. Okay. So, unless there is an external trigger, state 1 will continue to be in that same state. So, let us see the circuit, details of the circuit of the monostable multivibrator using an op-amp. The standard circuit for this monostable multivibrator is something like this. And I must say that it is the most complicated of the three multivibrators, this circuit. And the reason for that complication is that this monostable multivibrator lacks symmetry. So, this is the construction of the monostable multivibrator. There are two diodes, okay, D1, D2. The voltage drop across each diode is say equal to VD1 and VD2. These are the diode drops or diode voltage drops. Often, when we were discussing diodes, I mentioned that there is always a threshold voltage. A threshold voltage is also sometimes known as the diode drop. Rather than saying the threshold voltage of the diode, we often also refer to it as simply the diode drop. So, VD1 is the diode drop of diode D1, VD2 is the diode drop of diode D2. Now, say initially the output voltage, this VA, is high, okay, or in other words VA is equal to VL plus, where VL plus is the upper saturation voltage of this op amp. Now, this state, this VA equal to VL plus is the stable state, as we shall see. On the other hand, if we have VA equal to VL minus, that is the VA, that is the output voltage of the op amp, is equal to the lower saturation voltage, this is the non-stable or unstable state. Now, why is this so? So, here I have drawn, coming back to this main circuit, I have drawn a pulse. Say VA is equal to VL plus, the upper saturation voltage, and I introduce a pulse. Now, because this capacitor will not pass any DC voltage through it, it will only pass the high frequency components of this pulse. The voltage at this terminal or this terminal of D2 will be a sharp pulse like this, okay, a spike, kind of a negative spike. Now, because of this negative spike, what happens is D2 becomes momentarily forward biased, because as you can see, if I introduce a negative spike at this terminal of the diode D2, this terminal will become highly negative, whereas this terminal remains whatever voltage it had previously. As a result of this, D2 becomes momentarily forward biased, and this, because D2 becomes forward biased, this spike voltage is also transmitted to this non inverting terminal of the op amp C. Once this spike is transmitted to the terminal C, what happens? The voltage, suppose I call this V1 and V2, V1 minus V2 becomes momentarily negative. Now, once V1 minus V2 becomes momentarily negative, it was positive before this spike arrived, V1 minus V2 was positive. Now that this spike has arrived at terminal C, V1 minus V2 becomes momentarily negative, that is V1 momentarily, the voltage V1 momentarily goes to a very low value, as a result of which V1 minus V2 becomes negative. Once this terminal, the voltage V1 minus V2 becomes negative, then what will happen? Because op amp has very high gain, so once you feed a negative input voltage, the output at VA will invert. It will go from VL plus to VL minus. Okay. So, it is like this. If we we plot the graphs at VA, so this is my VA, it was V equal to VL plus initially. After the negative spike voltage arrived, it went from VL plus to VL minus. Okay. And what about VC? VC was also at a certain high voltage. Then when the spike arrived, it went low momentarily and stayed that point. Now the question is, what is this high voltage at VC? So let us come back to the circuit once again. So initially this voltage VC, the voltage at terminal C, was high. Now what was that value, the high voltage? To find out that high voltage, first note that initially this D2 was reverse biased. Okay. If this is reverse biased, that means no current will flow through the diode, and so then the voltage at VC is simply VA divided by R1 plus R2 multiplied by R1. So then I can say at this point the voltage VC was equal to R1 upon R1 plus R2 times VA, and this I am calling as beta VA. And since initially VA was equal to VL plus, so this was initially equal to VL plus. So this was equal to, this is the value of VC. So this is VC that I am plotting. Initially it was VL plus. Now after the spike arrived, what happened? All this happened momentarily. Once the spike arrived at port C, the voltage input, that is the voltage difference between the non-inverting and inverting terminal, became negative, and VA went from VL plus to VL minus. That is what I have shown here. Once VA become equal to VL minus, the voltage at C will be what? Now see, this diode had only momentarily become forward biased. Once the spike ended, it went back to a reverse bias state, that is no current will flow through it. And once this is reverse bias and this no current is flowing through it, the voltage at port C will simply be the resistive division of VL minus over these two resistances. So after the transformation of VA from VL plus to VL minus, VC now becomes equal to beta VL minus. So this voltage is beta VL minus. Okay. What about the voltage at point B? So far we have never talked about this, the voltage at terminal B. Now when initially when VA was equal to VL plus, the voltage drop at B was equal to the diode drop, isn't it? Because once if this is, if VA is equal to VL plus, then the only voltage drop that is present between point B and ground is the voltage drop across the diode, that is the threshold voltage of D1. So if I try to, let me take a fresh page then. So I have my VA going from VL plus to VL minus, this is VA. Then I have my VC going from beta VL plus to beta VL minus, and I have my VB, which was initially equal to VD1 okay. And then once VA transforms from VL plus to VL minus, so then what will happen? Now, VL minus is much more negative as compared to VL plus. Therefore, it will cause the voltage, once this voltage becomes equal to VL minus, it will cause the voltage at B to go down, okay, because this is very negative. So, it will drag down the voltage to a lower value. So, then VB will be dragged down like this, okay. But how long will it be dragged down? See, the voltage at VC is equal to beta VL minus after the transition. So, as long as the voltage at C is more negative as compared to the voltage at B, VA will continue to remain at VL minus, but VA being equal to VL minus is also dragging down VB continuously. So, at the point where VB becomes more negative than VC, what will happen is again VC will be at a higher value than VB, and again we will have a transition in VA from VL minus to VL plus. So, that is the thing, as long as VB is more positive than VC, VA will continue to be in VL minus, but the moment VB becomes more negative or equal to VL minus, what will happen is there will be a transition. Now that the non-inverting terminal of the op amp again becomes at a higher voltage than the inverting terminal. So, what we will have is again a transformation in VA from VL minus to VL plus like this. Once VA transforms, VC will also simultaneously transform from beta VL minus to beta VL plus, and once we have VA transitioning back to VL plus, okay, now let me come back to the circuit once again. Once we have VA coming back to VL plus, that will again cause the voltage VB, that will drag the voltage VB upwards, okay, and back to its stable value of VD1. So, VB after this second transition will slowly go on till it reaches the value of VD1. Now, this is the basic understanding of the circuit, but we also need to put this whole thing in a mathematical form. Now, first thing, some design issues that we have to consider is that this R4 has to be much larger than R1. So that this spike travels completely or as much as possible to this terminal C. If this R4 is a very low value, then this spike will actually drain out through R4. We do not want that. We want R4 to appear almost like an open for this spike. The second thing is, what is the total time that this pulse existed for, this negative pulse in VA or VC, what is the total time that it existed for. So, to understand that, let us write the equation of VB in this stage, that is when VA is equal to VL minus, okay. Then can I write VB as being equal to VL minus of VL minus of VD1, since VD1 was the initial voltage, multiplied by e raised to minus t upon R3 C1. So, here R3 C1 is the time constant, because this voltage at point B during the negative, when VA is equal to VL minus, the voltage at B is decreasing by a time constant given by R3 C1. So, this will continue till at t equal to t we have VB equal to beta VL minus. So, if we substitute this value of VB into this equation and then equate for this capital T, we will get an expression for the total time taken for the negative pulse, and that comes out to be okay. So, this is the total time for which the negative pulse of the monostable multivibrator exists. Okay. So, if suppose we ignore the diode drop, that is, if suppose VD1, we assume that VD1 is equal to 0, okay, we have T given by C1 R3 ln 1 upon 1 minus beta. So, we see that this time for the pulse depends on 3 quantities, I beg your pardon, depends on 4 quantities. One is R1, R2, C1 and R3. Usually, if the feedback components R1 and R2 are kept constant, so by modifying C1 and R3, we can obtain a pulse for a desired duration. Usually, monostable multivibrator is used as a timer, that is, it signals, it is used to signal the start and stop of certain events. For example, say if we apply the negative spike, coming back to the circuit once again, if we apply the spike, negative spike at the start of an event, okay, and adjust this R3 and C1, so that it coincides, the total time of the negative pulse of this monostable multivibrator coincides with the end of the event, then that will give us an accurate representation of how long the event really existed. So, that is one use of a monostable multivibrator, that it is used, often used as a timer circuit. So, in this module we learnt about the monostable multivibrator, I want to reiterate that monostable multivibrator does not have two stable states, neither does it have two unstable states. It has one stable state and one unstable state. In this case, the stable state was when the output of the monostable multivibrator was equal to VL plus, and the unstable state was when the output of the op amp was equal to VL minus. When the output is in VL minus or the unstable state, the input to the inverting terminal of the op amp will slowly be dragged down till it becomes more negative than the non-inverting input, and then once that happens, there is again a change of state at the output VA back to the upper saturation voltage VL plus, and this way the circuit returns to its stable state. In the next module, we will be covering about, we will be discussing about Zener diodes and the Zener effect. Thank you.